Hello everyone. Today we have our last talk will be given by Salih Erdem. His mentor is Eda Kırımlı. Now she will introduce him to us.
Hi, today Salih Erdem is gonna talk about the ring correspondence and KLTP algorithm. He's a double major student in CS and Mathematics at Boğaziçi University. It has been a great pleasure to work with him for me. And it's your turn, Erdem.
Okay, thanks. You can see the screen, right?
Yes.
Okay, hey everyone, this is Erdem, and today I'll be talking about the ring correspondence and the KLPT algorithm. Right. Okay. This is the outline for today. We are going to first look at the mathematical building blocks, and then the ring correspondence. Then we are going to look at the KLPT algorithm, just brief overview of it, and then we are going to look at an application of it, the sign signature scheme. So, what are quaternion algebras? A quaternion algebra over a field it's a central simple algebra, and it has dimension 4, and they generally look like this. Like they have dimension 4, and they are like the linear combination of k, ki, kj, and kk. And here, I squared is a, j squared is b, and ij is k, and ji is minus k, so it's not commutative. And we generally denote this quaternion algebra looks like this, like b is ab over k, where I squared equals a, j squared equals b. And this is like the general denotion for a quaternion algebra. And this is an example, actually, as far as I know, this is the first example of quaternion algebras, the Hamilton's quaternions. They satisfy the following formula, and I guess most of us familiar with them from physics. And okay, some definitions with quaternion algebras, and here these these definitions are going to be important for us. The splitting and ramification. We say a quaternion algebra B splits at P if B tensor product with Kp is the matrix algebra with Kp, and if the same tensor product is a division algebra, we say it ramifies at P. So a quaternion algebra is splits or ramifies at a P, and it's given by this relation of B tensor product with Kp is isomorphic to a matrix algebra or a division algebra. Okay, and another concept is order of a quaternion algebra. An order of a quaternion algebra B is a subring of B, and it's also a lattice. They are discrete and they are finitely generated. And another concept is the maximal order, and this is a concept that most of us is relative with, because like it's like the maximal ideal. So it's an order that is not properly contained in any other order. And another concept is the left O ideal or right O ideal of B, a quaternion algebra. It's a subset of B, and it satisfies this relation of OI is subset of I. And here O is a maximal order. And if a subset satisfies this relation, we say it's a left O ideal, and if it satisfies this, we say it's a right O ideal. Okay, and we can move to the elliptic curves here. So an elliptic curve is given by this equation, and it's defined over a field K. And if this characteristic of this field is not 2 or 3, we can give the elliptic curve from this equation. It's actually a more generic equation in general, but for our purposes in general, the characteristic will not be 2 or 3. So our elliptic curves will generally can be given by this formula. Here A and B are constants from K, the field that we are working on. And a concept with elliptic curves is the J invariant of an elliptic curve. And it's defined from this following formula. And this concept will be important because the J invariant classifies elliptic curves up to isomorphisms. So like for all elliptic curves isomorphic to each other over an algebraic closed field like a bar, their J invariant will be same. So classifies these elliptic curves of their J invariants. So if we have two elliptic curves, and if their J invariant is same, and they are going to be isomorphic. And here it's possible to define a group law on these elliptic curves. And okay, here to construct our group, our set is the points in these elliptic curves, like the points that satisfies this equation. So like here we can see these points like this. In general, if you define your elliptic curve over Q or R, you see your elliptic curve like looking like this picture. And you have one other point, a special point called point at infinity. And this point at infinity is a point that lies on all the lines that are orthogonal to x-axis. So on all the lines like this, orthogonal to x-axis. And this point at infinity will lie on all of them. This is a special point, and this is going to be identity element of our group. So how we do summation in this group? So in order to sum 2 points like this and this, what we do is we write the line going from these 2 points, we intersect with the curve, we take the symmetry of it, and this is going to be result of our summation. And here you can see some formulas relating to this summation of elliptic, the operation of elliptic curve. So it's possible to formalize this summation, notion of summation. Okay. Now that we talk about the basics of elliptic curve, we come to the isogenies. So what's an isogeny? An isogeny is a special type of mapping between elliptic curves. These mappings needs to be morphisms, and they need to preserve the point at infinity. So it's a special type of mapping between elliptic curves. And we can define a degree of an isogeny. So degree of an isogeny phi that are going from E to E prime is the degree of the corresponding rational function. Because this is a morphism, can be written by a rational function. So it has so it's the degree of this rational function will be the degree of an isogeny. But for finite isogenies, which is also the case that it is general for us in general, the degree of the isogeny will be the kernel of phi, the kernel of the isogeny. The size of the kernel of the isogeny, sorry. Okay, and another concept is the concept of dual isogeny. So for isogenies, we don't have always the inverses, but for any isogeny phi, we have a concept relatively similar to the inverse isogenies. So like you have, for any isogeny phi going from E to E prime, there is a unique isogeny phi hat going from E prime to E, such that the composition of both these isogenies is multiplication by some mapping, multiplication by M mapping, and here n is the degree of the isogeny that you are working on. So you have a concept relatively similar to the inverses, but not just that. We call it dual isogenies. And another concept here is the endomorphism ring of an isogeny of an elliptic curve. So for an elliptic curve, it is possible to define the set of isogenies going from the elliptic curve E to E again. And these isogenies form a ring. And the operations here are the summation of two functions, two isogenies. And the other operation is the composition of those isogenies as multiplication. And this set with these two operations forms a ring. We denote it by this endomorphism of E. And another concept that is the core of this presentation is the supersingular elliptic curves. Here, it is possible to characterize an elliptic curves endomorphism rings. There's a theorem about this. And one of the cases is an endomorphism ring of an elliptic curve can be a maximal order in a quaternion algebra. And if this is the case, we say that this elliptic curve E is supersingular. So like it is supersingular elliptic curves has lots of different definitions, but this is probably one of the first definitions of it. So if the endomorphism ring of an elliptic curve is isomorphic to a maximal order in a quaternion algebra, we call this elliptic curve supersingular elliptic curve. Okay, now that we look to the mathematical building blocks, we can look to the during correspondence, can look at an overview of during correspondence. Here, actually, what during correspondence says is, during correspondence gives you a connection between two worlds. What are those two worlds? One of these is the supersingular elliptic curves over FP squared, and the other is maximal orders in BP infinity, or what, and the B minus Q minus P here, minus Q depends, a constant depends on P, and, or we call BP infinity the quaternion algebra that is ramified at P and infinity. So for every elliptic curve, such elliptic curve, you have a such maximal order, and for every such maximal order, you have a such elliptic curve. This is the first term, the generic during correspondence, and it is also possible to come up with several other formulations of this during correspondence, which is going to be very relevant for us. Here we can look at an example. This is our curve, and this is the field, the prime that we are working on satisfy these relations. And the endomorphism ring of this curve looks like this. Here, I is the twisting automorphism and pi is the Frobenius morphism. And this endomorphism ring of this curve, it's possible to prove that isomorphic to this, and it's the maximal order in a quaternion algebra. Okay, now that we look to the ring correspondence, let's do a brief introduction of the KLPT algorithm. So what KLPT algorithm does is actually, there are several formulations of it, but one of the first formulations of it is you have a left or ideal I in a quaternion algebra, and the KLPT algorithm finds an equivalent ideal of a smaller norm. So you have a quaternion algebra. Maybe it would be easier if I show this. You have a quaternion algebra BP infinity, and you have a maximal order O, and you have a left O ideal, which is I, and it is not very nice properties, like its norm is not very small, and KLPT algorithm gives you a way to find another ideal, another left O ideal of this quaternion algebra, which has smaller norm. And this is important for us because when the ideal has smaller norm, it will be practical to find some isogenies between some elliptic curves. So this is the main use case of KLPT algorithm for us. And the significance of the KLPT algorithm is like this. So here maybe we can look at this picture. I said that the ring correspondence gives us a connection between two worlds, and the world of elliptic curves, there are several problems and they are really hard to solve. At least we believe that it is. It's hard to solve. But in the world of quaternion algebras, thanks to the KLPT algorithm, some of the problems are easier. Okay, now that we look to the KLPT algorithm also, we can look at a practical example of it, the SCHI signature scheme. SCHI is a digital signature scheme, and it's based on a finding path in an isogeny graph between two supersingular elliptic curves. It uses the KLPT algorithm to compute this isogenies in an efficient way. And it's a NIST competitor for quantum resistant digital signatures. Yeah. Okay. So what is the goal of SCHI? In SCHI, there's a prover and verifier. And prover is trying to prove that they know a secret isogeny between two public elliptic curves. Here, E0 is a public elliptic curve that's known by everybody. And EA is the public key of the person. Let's call him A. And EA is public key of it. It's an elliptic curve. And here, the prover says that they know an isogeny between E0 and EA. But they don't want to reveal this isogeny. So like they want to prove this, they want to prove that they know this isogeny, but they don't want to show this isogeny to anyone else. And SCHI gives us a way to do that. Gives us a way to prove to do this. So we have E0 and EA, and we have the tau discrete isogeny. So what prover does here is they first compute a random isogeny from E0, and let's call it psi, and they go to a random elliptic curve E1, and they keep this psi secret, and then they send this E1 to the verifier. And after this, verifier computes a challenge isogeny from E1 to E2, the phi from E1, and they end up in E2. And they send this E2 to the prover, and they keep this isogeny secret again. And they ask prover to give an isogeny between EA and E2. Here, normally, the prover is not able to, or anybody else is not able to compute an isogeny between two elliptic curves easily, because we believe it's hard and like it's not known a solution for this. But here, if the prover knows this secret isogeny tau, what they can do is they can construct this isogeny sigma, and it's like this. It's like the dual of tau, and then composed with psi and phi. They can, because they know this, and they construct this sigma, and they send this sigma to the verifier, and verifier checks whether this isogeny really corresponds and does the important metrics here. Verifier does this. And here KLPT algorithm is used because when when you want to compute, when you have a random isogeny from E0 to another curve, what you do actually is, because you know the endomorphism ring of this curve, using this endomorphism ring, because it's the public known elliptic curve and it's probably pre-computed, what you can do is easily compute another isogeny to it. Okay, and that's the end for me. Yes. I can take questions if there are any.
Thank you for the great presentation.
Yes. Erdem, challenge is always public. You just say secret.